Hey guys, Kenna here. So today we're going to go ahead and build on what we went over in terms of light last time so that we can go ahead and explore color. Now, we talked a little bit about the different parts of the EM spectrum, and when we were talking about light, we said we were focusing on the visible light portion. Now, when we see using our eyes, okay, if you remember the anatomy ed puzzle that you guys did, going ahead and taking a look at how the eye functions with our rods and our cones, we see different wavelengths as color. So we want to get a little bit more detail about how that works and why we see the colors that we do. So our essential questions for today. Number one, what is color and how do we see it? Number two, how does a color filter work? Three, how does color blindness work? And lastly, kind of tying all this together, hopefully, how does trichromatic color theory work with respect to color addition and color subtraction? So we'll take a look at how colors are produced in terms of the wavelengths that we see and how that's picked up by our eyes. Now, before we go ahead and jump in on the notes proper, I want to go ahead and show you a video, and this is going to go ahead and hopefully review some of the things that we've already covered in terms of waves, characteristics of waves, and then ultimately light. And then we'll go ahead and jump in on color.
One of the most striking properties about light is that it has colour. To understand the phenomenon of colour, it helps to think about light as a wave. But before we get to that, let's talk a little bit about waves in general. Imagine you're sitting on a boat on the ocean, watching a cork bob up and down in the water. The first thing you notice about the motion is that it repeats itself. The cork traces the same path over and over again, up and down, up and down. This repetitive, or periodic, motion is characteristic of waves. Then you notice something else. Using a stopwatch, you measure the time it takes for the piece of cork to go from its highest position down to its lowest and then back up again. Suppose this takes 2 seconds. To use the physics jargon, you've measured the period of the waves that the cork is bobbing on. That is, how long it takes a wave to go through its full range of motion once. The same information can be expressed in a different way by calculating the wave's frequency. Frequency, as the name suggests, tells you how frequent the waves are. That is, how many of them go by in 1 second. If you know how many seconds one full wave takes, then it's easy to work out how many waves go by in 1 second. In this case, since each wave takes 2 seconds, the frequency is 0.5 waves per second. So, enough about bobbing corks. What about light and colour? If light is a wave, then it must have a frequency, right? Well, yes it does, and it turns out that we already have a name for the frequency of the light that our eyes detect. It's called colour. That's right, colour is nothing more than a measure of how quickly the light waves are waving. If our eyes were quick enough, we might be able to observe this periodic motion directly, like we can with the cork in the ocean. But the frequency of the light we see is so high, it waves up and down over 400 million times a second, that we can't possibly see it as a wave. But we can tell, by looking at its colour, what its frequency is. The lowest frequency light that we can see is red, and the highest frequency is purple. In between, all the other frequencies form a continuous band of colour called the visible spectrum. So, what if you had a yellow pencil sitting on your desk? Well, the sun emits all colours of light, so light of all colours is hitting your pencil. The pencil looks yellow because it reflects yellow light more than it reflects the other colours. What happens to the blue, purple, and red light? They get absorbed, and the energy they are carrying gets turned into heat. It's similar with objects of other colours. Blue things reflect blue light, red things reflect red light, and so on. White objects reflect all colours of light, while black things do exactly the opposite, and absorb at all frequencies. This, by the way, is why it's uncomfortable to wear your favourite Metallica t-shirt on a sunny day.
Okay, so color. An object's color depends on the wavelengths of light that it reflects. You know that white light is a blend of all the colors of the visible light spectrum. And this image below shows white light striking a green leaf. Only the green light is reflected to your eyes, so that's what you see. All the other wavelengths are going to be absorbed, which makes sense because the leaf is going to use sunlight in terms of the electromagnetic spectrum, right, to go ahead and do photosynthesis. It absorbs a little bit in the ultraviolet as well, but what we start looking at is we start realizing that this whole process is about transferring energy, which we've already kind of discussed. So we got to go ahead and keep that in mind. Now, although some objects appear to be black, black is not a color. Okay, black is the lack of light being reflected back. So no color essentially is what black is. So this is counterintuitive because we think about it usually in terms of crayons or colors, right? And when you color, there's a black crayon. Now, that black crayon, however, is doing something a little different in terms of color subtraction, which we'll talk more about when we go ahead and get to color addition and color subtraction at the end of these notes. So objects that appear black absorb all the colors and reflect little to no light. But white objects are reflecting all of the light, or the full spectrum is reaching your eyes. And as such, you are seeing all those different wavelengths together. Now, the color of an object depends not only on what it absorbs and reflects, but what types of light are actually being projected originally. So if it's not white light, then we have to go ahead and think about how that looks. When you see a notebook like this red, this is red because white light hits it and it absorbs all the wavelengths except the red wavelength. So only red light is being reflected back. Now, if we do this and we have a pair of purple pants and assume this is a white hat, it took out the filling here, so it's not perfect. But when you look at this, if you have purple pants, what is being reflected off of it? Well, hopefully you said purple light. We talk about it in terms of violet, maybe depending on the dye, some red, some blue, because we'll perceive that as well. But a white hat is going to reflect all of the colors off of it. Okay, so this is what we need to understand. But if we start to look at something in colored light, it might look a little different. Now let's start by looking at this soccer kit. Okay, we've got a nice red top and a nice kind of blue purple pants. And when you go ahead and start looking at that, the white light comes in. Those are the colors that are reflected off of it. Therefore, that's what you see. Shirt looks red, shorts look bluish. But what if you were to go ahead and show it in red light? If you only put red light on it, then obviously the top of the kit is still going to look red. But if you go ahead and take a look at the shorts, how are they going to look? Now, if it's not going to reflect red, it's going to look like nothing's reflecting off of it, and therefore they're going to look black. With the reverse, if we go ahead and use the blue light, the shorts are going to go ahead and look blue, but the top, because it won't reflect any light, is going to look black. Okay. And so this understanding of them is a little bit more difficult to kind of grasp than just everything's hit by white light. So depending on what kind of wavelengths are coming in, then we can go ahead and predict the color of an object based on its pigments and what it's going to reflect back. We see the light that is reflected off of it. So in this first example, we're looking at some red socks. If we hit it with red light, the socks appear to be red because that's the color that it naturally reflects. But if we go ahead and shine it under blue light or green light, the socks are going to look black because we're not getting any light reflected back off of them. Now, if we have a blue teddy bear, red is not the color of it. And so if we shine red light on it, it's going to look black. So what is it going to look like if we shine it under blue light? What about green? Pause the video here and take a minute to go ahead and think about what these other colors are going to look like. Then we'll go ahead and double check them just so that you make sure you understand how this works before moving on. Okay, so welcome back. Hopefully you've had a minute to go ahead and think about what these other ones would be. Let's go ahead and go through this together. Now, the teddy bear is blue. So in the blue light spectrum, this is actually going to still look blue, okay? Because that's the color that it is. But if we put it under green light, it's going to look black because That's part of our problem. We start looking here is that there's nothing reflecting off of it if green light's the only thing coming in. If we look at a green camel, put it in red light, we should be looking at black because it doesn't reflect it. Blue's going to be the same. And then when we go ahead and get to green, green is going to look green. This one's a little trickier. If we're using our standard RGB color scheme and we're trying to project a magenta book, okay, that's going to go ahead and under red light look red because there is a certain amount of red in the magenta that we're looking at. If we go ahead and project it under blue, it's going to look blue. But under green, because there's no green in magenta, it's still going to go ahead and look black. Okay, so let's go ahead and talk about how filters work and how you might get these red, blue, green, different colors in terms of the light rather than reflecting them as an object might. Okay, so when you do filters, a filter basically absorbs or reflects the different wavelengths of light, but only lets one pass through it. So if we have blue glass, it looks blue because it absorbs or reflects the other wavelengths and allows the blue to pass through it, which is what's making you see the blue. Okay. But you may be asking yourself as we're having this discussion about color and seeing color, well, does everybody see the same thing? Well, to a certain extent, no, right? Because we know that there are people like me who are colorblind. And so what is colorblindness? Well, it turns out that if one or more of your sets of cones doesn't properly function, you're not able to distinguish between certain colors. Now, most people who are said to be colorblind are not truly blind to color, me included. I can actually see a fair amount of color, but I have difficulty distinguishing between several colors. Most commonly red and green. I do have red and green, not so much fire engine red and forest green, but especially the pastel colors. The lighter reds and lighter greens look very similar to me. Um, Another example of this is that I have a tiny bit of blue purple, just depends on the shade. And I still have a little bit of green brown, again, depending on the shade. Forest green and like dirt brown are still pretty easy for me to identify. It's those certain tones that are kind of a little more indistinguishable that I struggle with. Now, some people have fewer than 3 types of receptors. We typically talk about these, and we talked about the fact that you have your RGB, and they're not actually red, green, and blue, but they cover a wavelength range, and they actually overlap a little bit. But when we start looking at color blindness, or what's more commonly known as color deficiency, it's less common in women because red and green receptor genes are actually carried on the X chromosome, and women have 2 of them. Okay. These are the ones that typically go wrong. And so the only way you can get a colorblind female is if they have 2 bad X chromosomes to have this deficiency, which is much less likely to happen. So let's go ahead and watch a little video talking a little bit about colorblindness.
Hey, and welcome to Brain Stuff. I'm Josh Clark, and this is the Brain Stuff where I explain to you how colorblindness works. Have you ever been looking at a rainbow and thought, man, what is it like to be colorblind? That's a really weird thing to think, but here's your answer. First, though, we should say it's actually not called colorblindness. The preferred term is color deficiency. So let's get a little more PC, shall we? Now, before we understand how color deficiency works, we have to understand how regular color vision works. And in humans, it's called trichromatic vision because we rely on 3 different types of cones, which are specialized cells in the eyes that contain photopigments. And the photopigment is a protein that's sensitive to a certain wavelength of light, aka a color, right? So these 3 types of cones are attuned to short wavelengths, which picks up blues, medium wavelengths, which picks up greens, and long wavelengths, which is in the red band of the visible light spectrum, right? So when everything's operating correctly, our eyes are exposed to light, and the different cones send information to the brain to let it know what kind of quality and amount of the type of light that it's sensitive to, it's receiving right then. The brain takes all this information, puts it together, and all of a sudden, these 3 different color informations equal 1,000,000 different shades of colors that we're capable of seeing. But what happens when it goes wrong and you have color deficiency, not color blindness? What you have is what's called anomalous trichromacy, which somebody said is the most beautiful combination of words in the English language. I think it was that. In most cases, color deficiency is the result of cones just not operating quite right. And most of the time, it's either the red cone or the green cone. And the problem is that either the red cone or the green cone will mimic the other one. Rather than enhancing the cone that it mimics, it actually cancels out or mutes the information from the other cone. So the sum total effect of all this is that the good information coming from, say, the green cone is being canceled out or muted by the mimicky information coming from the red cone. And since the brain uses these different shades to make more colors, a lot of different stuff seems kind of dull or gray. That's color deficiency. Well, in particular, that's anomalous trichromacy, the most common type of color deficiency. The reason for all of this is genetic mutations, actually. Both of the genes that lead to the expression of cones in our eyes are found on the X chromosome, which is contributed by the female, aka your mom. Now, if your mom has a mutation on one of her genes, you have a 50% chance of some sort of color deficiency. If she has a deficiency on both genes, you have a 100% chance of having a color deficiency, which is what's called a certainty. And what's even stranger is that a lot of people who are red-green color deficient don't know that they are until they're tested for it. Luckily, there are ways of curing this. There are contacts and glasses that can correct a little bit of the color deficiency, so you don't have to walk around feeling so glum and that everything's just kind of gray. So now you know about how color blindness works. Thank you for sticking in there with me. This is a pretty neat one if you ask me. Now go forth and check out rainbows everywhere. And while
Okay, so I'm going to go ahead and move on. Now, as a colorblind person, it's not as easy maybe to get a hold of those glasses or contacts as you may think, and we can function just fine without having assistance for colors in most cases. You know, if I'm trying to make a really nice matching outfit, I just ask my wife for help with it. When I'm going with colors, there could be a little tension sometimes because it's like, this color looks good to me to paint the house, but my wife says, no, that's not a good color. We're not painting the house that color. And so, you know, there are some things to kind of work out through that. But you know, it is something that is very doable. Now, they talked about some of those colorblind tests, and it's interesting because this is actually how I found out I was colorblind. I guess I already had known, or my parents had already known, because apparently I'd swapped green and brown when I was coloring grass and trees when I was in kindergarten. But it never really came up for most of the things that I did. It came up again when I started looking at going to college. When I was looking at going to college, I originally wanted to be a pilot. I wanted to go into the Air Force and learn how to fly jets. But it turns out that you don't actually get to fly jets if you're colorblind. I guess there's such a complicated dashboard with so many different colors of lights that that's just not an option. You can't fly commercial aircraft or military aircraft if you're colorblind. So switched jobs and started looking at other careers. And then I started deciding I wanted to be a chemical engineer. And then I went to college and started working on it. And then in one of my later labs for organic chemistry, we started trying to go ahead and do some titrations. And I had trouble with the colors in the titrations. And they told me, you're never going to be a chemical engineer. You have to do tons of titrations and you can't see enough color. So time for career change again. And so then I switched into biochemistry. When you're starting to look at macromolecules and proteins, color isn't as big a deal because these are tiny little structures. Anyway, what is it like to be colorblind? Well, it's hard to get you to really experience it, but this video at least attempts to help you understand what it's like to be colorblind. Enjoy.
I'm Judy Befaro.
Hello, I'm Patrick. My name is Andrew Hayter, and I am colorblind. It's not that I can't see colors. I can see most colors, but it's that certain colors fade into what I would call indistinct.
The analogy I always use is that if you have a pack of 36 colored pencils, I can only see maybe 12 shades of those colored pencils.
We're trying to do those dot tests where they have the different numbers and it's like in a different color. But trying to do these, everyone will be like, oh, it's a 7, oh, it's a 62. And be like, you're all lying. Apparently there's one with a sailboat and I've never seen it.
I play soccer. It may affect me on the field. Our team is purple and the other team was a different shade of purple. And I passed to the other team 2 times.
I'll often be shopping for something and just go up to a stranger and ask them, is this black or is this navy blue? Is this red or orange? That kind of thing.
Like you can tell right here, I'm wearing a green sweater, but if you start like asking me like, what shade of green, I'm the worst at it.
So the stop, don't go hand for crossing the street and the walk, time to go. I see the hand is red and I always thought that the man was green. That's a context clue thing where I was like, oh, okay, one's red, one must be green. But someone told me that the man crossing the street is white.
I like to think that I have some sort of like advantage by having a disadvantage.
I suppose I may be missing out on things. I guess I don't know what I'm missing out on.
And it's kind of cool too because I don't view it as very limiting, but then when people are just always so intrigued by like, what is this? Like, how does it even work? Do I only see like black and white like a TV show, or is it, you know, which is not true.
Like last night, my friend asked me, I was like, I'm doing this interview about color blindness, and he goes, what color's the couch? And it's bright red. Usually, because it's kind of annoying when people are like, oh, well, what is this? And it's not that big of a deal.
Okay, so you get kind of an idea in terms of how this works. And so the next thing I thought I'd do is I'd go ahead and give you a chance to go ahead and take one of these color blindness tests. So the colors may not be perfect, depends on the settings of your monitor as you're going to go ahead and watch it. And I've gone ahead and put the link down here, so if you want to try this for yourself, you can. Okay, you can run it on your family members and see if they have any anomalous trichromacy. So we'll go ahead and let this run, but please go ahead and try and do your best and see if you can actually see them. All right. So 3 seconds, okay? Try it in 3 seconds. Yeah, I can see that one. A little difficult, more difficult, but I can see it. I can still see it. Yeah, I can't see this one at all. Okay, I can see this one. Nope. Yeah, I can see this one. It's harder, but I can see that one. Yeah, maybe, kind of. No, not so much. Okay. So. Okay. So you get the idea, but you're going to kind of look at yours. So the next thing I want to go ahead and do is have you watch this one. And there's a key word I want you to take away from this, and that's qualia. And we'll talk a little bit more about it after we go ahead and watch the video. You know what? I think I'm going to go ahead and leave this for an Edpuzzle, so you can go ahead and pop out and watch that instead. There's a lot of cool stuff in this video, and then really want you to understand that term qualia and how it relates to our perception of the everyday world, not just with color, but with many other things, finding that own internal perspective, I think it is, and nobody's going to ever be able to feel or understand the way you experience the world around you. Okay, so go ahead, pause the video here, go ahead and watch that Edpuzzle, and then come back and finish. Welcome back. Did you like it? It's pretty cool, huh? Well, I hope you did. I don't know if you've seen those before, but I like that group Veritasium. So Now let's go ahead and look a little bit closer at trichromatic color theory. It's come up in a couple of the videos that we've watched, but we need to make sure that we really understand what trichromatic color theory is. So according to this theory, also known as the Helmholtz theory of color vision, there are three receptors in the retina that are responsible for color perception. And we talked about them before as the cones. One receptor is sensitive to the color green, the other one to the blue, and the other to the red. Now, again, remember, it's not just that color. It's a range of colors, and there's actually some overlap between the different cones. But these three colors can then be combined to form any visible color in the spectrum. The identification of these three receptors responsible for vision did not occur until 70 years after the theory was proposed. Researchers discovered that cone pigments have different levels of absorption. Cones, remember, are the receptors located in the retina that are responsible for vision of both color and for detail. Okay, but it needs to be bright in order for you to be able to really do a good job of differentiating between these. The cone receptors differ in absorption amounts due to the amount of opsin amino acids in the receptor. Now, you're not going to be responsible for that, so don't worry about that term. I'm just trying to give you a picture. The three different cone receptors are the short wavelength cone, what we call the blue cone, the middle wavelength cone, which is known as the green cone, and the long wavelength cone, which is known as the red cone. Okay, and so this is part of where we come up with the system for the RGB color schemes that we see in a lot of like the monitor that you're looking at right now to go ahead and watch this. Okay, so what that tells us though is that we can go ahead and use the light range or the color wavelengths that come into our eye to go ahead and produce pretty much any color that's out there. But there are two ways to do this. One is what's called additive color, where we're going to combine light rays. And the other is what's called subtractive color, where we're going to remove certain light rays. And so I have little videos to go over both of these as well. And now the gentleman's voice that's in these is not always the easiest to listen to, but he does a really good job of articulating the two different processes. And so please kind of pay attention as you're going through, and then we'll go ahead and talk a little bit about it.
This is the first of 3 demonstrations designed to help students understand the tri-stimulus theory of color perception. Whilst this theory forms the basis of color reproduction technology in photography, film, television, and printing, it is by no means the complete story of how color perception works. However, we will use the theory to explain how the mixing of different light colors is achieved. While color perception science is in fact far more complex than what is presented here, this will serve as an introduction to the principles used in achieving a relatively complete spectral range of color using 3 primary colors in the case of projected images and television screens. In mixing colored light, I begin with a dark screen onto which I have projected the white text you see and left the rest of the screen blank. The 3 primary light colors or primary additive colors are red, green, and blue. Red stimulates the retinal cells in the eye that we call the red receptors or red cones. Green stimulates the retinal cells in the eye that we call the green receptors or green cones. Blue light stimulates the retinal cells in the eye that we call the blue receptors or blue cones. When the red and blue cones are both stimulated, we see magenta. Red light plus blue light produces magenta light. Magenta is a secondary additive color. When the red and the green cones are both stimulated, we see yellow. Red light plus green light produces yellow light. Yellow is a secondary additive color. When the blue and the green cones are both stimulated, we see cyan. Blue light plus green light produces cyan light, and cyan is a secondary additive color. Here I have the three primary colors projected with secondary colors appearing where any two colors overlap. But now for the first time we see the black screen has become white where all three of the primary light colors are projected. Primary red plus primary green plus primary blue add up to white light. Now we have seen the primary and secondary colors of light. I want to take a brief look at complementary colors. In the RGB color system, RGB color is another way of referring to additive color. The complementary colors to any of the primaries is a secondary color. When I add together complementary colors, I get white. Here, the red has a complementary color cyan. When you add those two together, you get white. When you add blue light and its complementary yellow light, you get white. When you add green light to its complementary magenta light, you get white. As an experiment, I want you to fix your eyes on the black spot in the middle of the white space for 30 seconds, starting now. I will let you know when the time is up. Resist the temptation to look around and try to keep the dot focused. If you go cross-eyed, bring your focus back to the dot. You should notice things happening around the rims of the colors, but keep focused on the black dot. What is happening is that the green cones are tiring in the area where green is falling on your retina, and the same thing is happening to the areas where blue cones are being stimulated and where red cones are being stimulated. When the screen changes to white, keep staring at the same spot. What you are now seeing is the complementary colors of the ones you have been staring at.
Okay, so now we're going to go ahead and take a look at subtractive color. How did that work out for you guys? If you really do a good job of staring at the dot, it really is cool to kind of see the after effect that's produced from the tiring of the cones. Okay, so let's go ahead and take a look at a similar video, this time going over subtractive color. Notice the differences in terms of the primary and secondary colors between additive color and subtractive color.
This is the second of 3 demonstrations designed to help students understand the tri-stimulus theory of color perception. While this theory forms the basis of color reproduction technology in photography, film, television, and printing, it is by no means the complete story of how color perception works. However, I will use the theory to explain how the mixing of pigments, dyes, inks, and paints is used to achieve different colors. When we considered additive color, we thought about mixing the different colors of light. We added the colors together. In order to understand the distinction between additive and subtractive color, it is important to remain focused on light. Though we are adding paint colors to each other, we are increasing the paint's ability to absorb light, and the new color is achieved by subtracting some light. In the additive demo, I started with a dark screen onto which I projected colored light. In mixing colored pigments, I begin with a white screen that represents white paper onto which I shall apply different subtractive primary pigments. The 3 primary pigment colors, or primary subtractive colors, are yellow, magenta, and cyan. The yellow pigment absorbs blue light, allows red and green light to pass through or reflect from its surface. We perceive the red and green light and see yellow. The magenta pigment absorbs green light, allows red and blue light to pass through or reflect from its surface. We perceive the red and blue light and see magenta. The cyan pigment absorbs red light, allows green and blue light to pass through or reflect from its surface. We perceive green and blue light and see cyan. Yellow ink absorbs the blue light. Cyan ink absorbs the red light. Thus only green light remains. Green is a subtractive secondary color achieved by mixing two primaries. Yellow ink absorbs the blue light. Magenta ink absorbs the green light. Only the red light remains. Red is a subtractive secondary color achieved by mixing two primaries. The magenta ink absorbs green light. Cyan ink absorbs red light. Only the blue light remains. Blue is a subtractive secondary color achieved by mixing two primaries. When all three of the primary subtractive colors are in the mix, primary yellow absorbs, i.e. subtracts the blue light, primary magenta subtracts the green light, and primary cyan subtracts the red light. With all the light absorbed, we see black. White light minus red light minus green light minus blue light is no light. Notice that the secondary colors derived from mixing any two of the primary subtractive colors are the same as the additive primary colors. Red, blue, and green are additive primary colors. Red, blue, and green are secondary subtractive colors. Yellow, magenta, and cyan are primary subtractive colors. Magenta, yellow, and cyan are secondary additive colors. That is the theory. In reality, when we mix the three primary subtractive colors to get black, we actually get something that's not quite black. So the printing industry uses a CMYK color space. K is black ink added to the three primaries to compensate for the inadequacy of the primary inks. Now we will do the same experiment we did with the additive after images. Using the subtractive colors, fix your eyes on the white dot in the middle of the black space for 30 seconds. Starting now, I will let you know when the time is up. Stay focused on the white dot until the screen turns white. "20 seconds. You are seeing the complementary colors complementary to the ones you've just been looking at.
Okay, so now you've seen additive and subtractive color. The primary colors for light, so additive color, are RGB, red, green, and blue. The primary colors for pigment, however, are the CMY, cyan, magenta, and yellow. And the secondary colors for light are the primary colors for pigment, and the secondary colors for pigment are the primary colors for light. And so keeping those straight is pretty cool. And then keep in mind the CMYK. If you have a printer that prints in color, it probably is using the CMYK scale. And because we can't get a true black from CMY, it's imperfect in terms of our dyes, then they add the gray pigment or the gray ink, the black pigment or the black ink to go ahead and give you the black color. So the sensation of color is actually caused by the brain. And as we saw with the video over qualia, your perception of a color may not be the same as somebody else's perception of the color. And you can actually create color on your own through the pressure on the eyelids, through dreaming, through hallucinations. But the main way to get color, the way we typically think of color, is through the presence or absence of light of various wavelengths. Now, light could be produced in different amounts at different wavelengths compared to, say, the sun or a fluorescent light bulb. Light could be differentially reflected depending on what pigment we're using, the CMYK system or some other mixture. It could be differently refracted or bent depending on if it's going through a prism like you see here on the left. Wavelength depends on specular reflection. Shiny copper penny, most metals actually, will go ahead and give you pretty clean specular reflection. And we'll talk more about these types of properties as we get into our next unit, going over these properties of waves. The last thing I want to introduce a little bit is fluorescence. Now, light at invisible wavelengths is going to be absorbed and re-emitted at visible wavelengths. Now, do not confuse this with luminescence. Now, in living systems, sometimes you'll see what they call bioluminescence. That is a chemical reaction that is releasing light. Fluorescence is the absorption and re-emission of an invisible wavelength as a visible wavelength. And you can kind of see this when you do a little bit of, say, a glow-in-the-dark t-shirt or something like that. So color appearance is strongly affected by, well, at least other nearby colors, adaptation to previous views, as you saw in the examples with the added subtractive color where we saw those after ghost images, as well as the state of mind. And so you don't want to write off uh, effects like hallucinations or psychedelic drugs, these types of things, because they actually do change the physical perception of color. Uh, and, you know, I typically here go ahead and show you a whole bunch of different eye tests that kind of play with your vision. But I'm going to go ahead and stop that here. It's not something that is really super beneficial at a distance, but you can try going online and finding a whole bunch of these kind of eye trick tests related to color. Um, some of the ones that I remember the most are the ones where they have the X's and the words green, blue, yellow, and they start out in the same color, but then they switch to different colors. And being able to say it, your brain has a hard time processing it because you get in habits and patterns as you go ahead and see it. Um, so I hope you took something valuable away from this. Stay healthy, stay safe, and I'll talk to you guys soon. Take care of yourselves. Bye bye.